May we have, may we have your attention, please? Welcome to Sanders Theater. We ask that you turn off all cell phones and other electronic devices. The use of flash photography is prohibited. Please take a moment to identify the nearest exit. In addition to the 6 regular exits, there are 2 emergency exits located at the back of the mezzanine and balcony levels. Thank you.
She looked up and saw something the world had missed. Vera Rubin's discovery changed the way we see our universe. By measuring how galaxies spin, Rubin provided the clearest evidence yet for dark matter, an unseen force shaping everything.
Far out, where there is no obvious stars, the rotation velocities stay high. And that's the evidence that there's dark matter.
Decades later, missions like NASA's Chandra X-ray Observatory, James Webb Space Telescope, and many other telescopes continue this legacy, illuminating the invisible from dark matter to black holes. Today, we map where dark matter bends space, where galaxies collide, and look to future questions of the universe. Vera Rubin saw the invisible, and now we see farther than ever.
Sometimes it takes a long time for the answers to come. Everything in the universe is evolving.
Good afternoon, everyone. Thank you so much for coming to celebrate the launch of the new quarter honouring Dr. Vera Rubin. We're delighted that you're here to join us today. We've got a really special day for you, and it is a great honour and privilege to be able to welcome you here to Harvard's Sanders Theatre on this day. I'm also delighted to welcome members of Vera Rubin's family. We have 2 of her grandchildren here today. We've got Ramona and Illyria. And so I want to extend a special thanks to the family for coming here today. It's a really special event for many of us in astronomy, and I'm sure it's an extremely special event for members of Vera's family. So thank you so much for coming. I'm also delighted to welcome Elizabeth Babcock. She is the director of the Smithsonian American Women's History Museum. And also we have a very special panel for you today who you'll hear about a little bit later. But I want to do a very special welcome to Katie Coleman, who's an astronaut. And she was one of the astronauts who helped launch the NASA Chandra X-ray Observatory and put it out into space. I'm Lisa Cooley. Yes, you can. Absolutely. I'm Lisa Cooley. I'm the director of the Center for Astrophysics, Harvard and Smithsonian. We are here in Cambridge. We're just up the street, 15 minutes walk away on 60 Garden Street. Come by if you are interested in the observatory. We have 800 astronomers, engineers, telescope and technical staff, and we are one of the largest astronomy organizations in the world. We operate telescopes in Hawaii, in Greenland, and in Arizona, and we're partner in telescopes in Chile, including the next generation telescope, the Giant Magellan Telescope, which is due to come online in 2033. Our astronomers are tremendously excited to be able to use data from the Vera Rubin Observatory, which has just started coming in. I hope you've all seen pictures from it released in the news. And so we're absolutely thrilled to have this opportunity to celebrate Vera Rubin, her life, and also the release of her quarter today. So the Dr. Vera Rubin Quarter is part of the US Mint's American Women's Quarters program, and honorees for these quarters are chosen by the Secretary of Treasury in partnership with the Smithsonian American Women's History Museum, the National Women's History Museum, and the Congressional Bipartisan Women's Caucus. When choosing a location for this celebration, it seemed only natural to host the event at a fellow Smithsonian institution. So we are the Smithsonian Astrophysical Observatory as well as the Harvard College Observatory combined together into the Center for Astrophysics here in Cambridge. And this is also part of a university where Dr. Rubin received an honorary doctorate's degree in 1988. We tried to recruit her into our graduate program and she declined. Vera Rubin's life is marked by an incredible passion for astrophysics, a determination to overcome barriers, and a real incredible trailblazing spirit. Her high school physics teacher told her to become an artist instead of a scientist. And we've come a long way because, in fact, my teacher told me to become a scientist and not an artist, which is what I wanted to do. And after an undergrad degree at Vassar in astronomy, she applied to Princeton to the PhD program, but she was declined because they didn't accept women at the time. She was accepted to the Harvard grad program, as I mentioned, but she declined, much to the disappointment of the director at the time, and she chose to attend Cornell University because her then fiancé was a grad student at Cornell. She went observing at telescopes that didn't have women's restrooms. She was the first women's astronomer who observed through those telescopes. At one of the telescopes without the restroom, she cut out a triangle from a piece of paper and stuck it on the restroom man sign and said, "All right, there, now we have the women's restroom." She gave a talk at the American Astronomical Society just after having had a baby 3 weeks earlier, which is quite a feat. Her research measuring the rotation curves of galaxies, so this is how the galaxies rotate, provided observational evidence for dark matter. And so what she found really was that galaxies would actually fly apart if there wasn't something else aside from the matter that we can see holding the galaxies together. And we call that dark matter. Does anybody know what dark matter is? We have astronomers in the audience. You notice they don't have their hands up either. We don't know. None of us knows what dark matter is. We know there is something there because galaxies, like what Vera Rubin found, they move as if there's more material there. We also know that galaxy clusters behave and light bends around clusters as if there's more matter there. Another piece of evidence that was found later for dark matter. But Vera Rubin found the first piece of evidence for dark matter. She also discovered peculiar motion, and that was first dismissed as invalid. Later, it was found out to be true, and in particular, she discovered a peculiar motion called large-scale streaming. So it's basically how streams of material and galaxies are moving in the local part of the universe. And she was also one of the first astronomers to discover the supergalactic plane. This is an enormous flattened structure that's about 1 billion light years across, and our galaxy is just part of that supergalactic plane. So any one of these discoveries would have been considered incredible and would still be considered incredible for an astronomy career, would have produced lots of awards and prizes, would have enabled that astronomer to become a member of multiple academies. But she made 3 incredible discoveries, and there are actually many more. If you look at her astronomy track record, she has many publications which have an enormous amount of citations, which means that many astronomers have been and are still using her work today. She received so many awards, I'm not going to talk about them because it'll take my whole 3 minutes that I have, But I personally think she should have won the Nobel Prize for her work. However, I'm delighted that she has been recognized worldwide and indeed throughout the solar system. She is a region on Mars has been named the Vera Rubin Ridge. There is the COSPA, or was the COSPA Vera satellite. The American Astronomical Society has named a Vera Rubin Early Career Prize. In Star Trek, there is a nebula. You need to see which episode that is, called Vera Rubin. Was named after her. And last year, NVIDIA announced that its next generation of data center accelerators will be named after her, with the CPU being named Vera and the GPU being named Rubin. I love it. And I hope you all have seen the beautiful images from the brand new Vera Rubin Observatory in Chile, which is going to be taking exquisite images of the sky every night. And astronomers all over the world are tremendously excited to be able to use that data. And finally, we have the new Vera Rubin Quarter. We're tremendously excited today to be celebrating the Vera Rubin Quarter. I think it's a wonderful celebration of her life and her achievements. And I'm sure if she were here today, she'd be incredibly proud. The honorees chosen for these special edition quarters demonstrate what can be possible with determination, perseverance, and indomitable spirit. Vera Rubin was the embodiment of all these traits. She truly paved the way for many astrophysicists, and she was a guiding light for many young people who worked with her. Her discoveries pushed forward the boundaries of astrophysics and our understanding of the universe. And during our panelist discussion today, we're going to have the opportunity to hear from a fellow astronomer who had the privilege of collaborating with Dr. Vera Rubin, as well as an astronaut who physically took the study of dark matter to space. So Vera Rubin's legacy continues to live on and inspire research today. And may this quarter, which I have one in my pocket, may this quarter inspire future generations to reach for the stars as well. Thank you again for being here today. I now have the honor of welcoming to the stage Vera Rubin's granddaughter and Harvard alumni, Ramona Rubin.
Good afternoon, everyone. Thank you for gathering here today to celebrate the release of the Dr. Vera Rubin Quarter and honor my grandmother's extraordinary legacy. Being here together, I'm reminded of something my grandmother would have loved to point out to us. The way that we're all connected across time and space in ways we rarely pause to consider. The galaxies she studied are so distant that their light traveled for multiple millions of years to reach us, to reach her telescopes. The elements in our bodies were forged in the hearts of stars billions of years ago, and the curiosity that drove her to peer into the cosmos connects us to every human who has ever looked up at the night sky and wondered. My grandmother had this remarkable ability to find wonder in both the vast and the intimate. I remember standing with her in Wyoming in 1986, watching Halley's Comet. I was 9 years old, and as she explained the comet's 76-year orbit, she calculated how old I would be when it returned. That night perfectly captured who she was, someone who could make the grandest cosmic phenomenon feel personal and immediate. What strikes me most about her legacy isn't just her scientific discoveries, though they fundamentally changed how we understand our universe. It's how she showed us that there's no conflict between rigorous science and pure wonder, between analytical thinking and spiritual awe at the cosmos. She taught me that you can be disciplined and systematic while still being amazed by the grandeur and bigness of everything. She also showed us that obstacles were simply problems to be observed. You heard about Palomar Observatory when they told her she couldn't observe because there was no women's restroom. She didn't see it as a barrier. She took it as a logistical challenge. She cut out a paper skirt, hung it on the bathroom door, and got back to her science. That's who she was, practical, determined, and always focused on the questions that matter. My grandmother grew up in an era when women had to fight to seek answers to questions about the universe. Today, we're honoring her on currency that will pass through millions of hands, carrying her story into countless everyday moments. She would be deeply moved by this recognition, but what would matter most to her is whether this small change in our pockets helps create real change in our world, whether young women look at this quarter and think not how amazing that one woman broke barriers, but simply science is a place where I belong. The Vera Rubin Observatory in Chile has just begun its mission with stunning first light images, continuing her work of revealing the universe's hidden mysteries. And our family dinner table was another kind of observatory, where she showed us that curiosity could be a career, and that seemingly disparate, separate systems are often deeply connected. Her concern for preserving dark skies for observation taught me to think about how human-made light affects not just telescopes, but sleep cycles, wildlife migration, and community health, insights that led me towards my own work bridging nature and public health. In just a few minutes, you'll hear from distinguished scientists about the profound and lasting impact of her discoveries on our understanding of dark matter and galactic structure. But before we dive into that, I wanted you to know the woman behind the science, someone who taught us that excellence comes from diversity of thought and experience, that the biggest questions require both intellectual rigor and childlike wonder. She would be thrilled to know that her work continues in a new generation of scientists who keep asking the questions that matter, to keep looking up at the stars with the same curiosity that drove a young girl from Philadelphia to reshape our understanding of the cosmos. On behalf of the Rubin family, I would like to thank you all, and I hope you enjoy today's presentation and celebration. It is my pleasure to now introduce Dr. Elizabeth Babcock, the director of the Smithsonian American Women's History Museum.
That was a lovely tribute. Thank you all so much for being here. My name is Elizabeth Babcock. I'm the director of the Smithsonian American Women's History Museum, and it's just an absolute honor to be here to celebrate the Rubin family's wonderful member and your specific grandmother's life and legacy. Thank you so much for those words. So Lisa Cooley, thank you also. Really appreciate it. You and the Harvard Smithsonian Center for Astrophysics for hosting us here today in this absolutely extraordinary space where discovery is being made and shaped and shared every day. So being here with you all today, surrounded by scientists and students and storytellers and educators, is a powerful reminder that history isn't just something that we preserve, it's something that we share and pass forward. And thank you also to the wonderful partners at the United States Mint. We're now able to share that history and those stories in a very powerful way through the American Women Quarters program. So at the Smithsonian American Women's History Museum, we're working to expand the story of America by shining a light on all of the lives and contributions of women whose stories too often go untold. Dr. Vera Rubin is one of those trailblazers. As you heard, her research offered the first persuasive evidence of dark matter and forever changed how we understand the universe. But she also changed the field through the ways that she actually moved through it. She overcame challenges, she asked bold questions, and she advocated for greater inclusion of women in science. This coin that we're celebrating today honors more than what Vera discovered. It also honors how she lived, and it's a constant and very tangible reminder that there's still so much more to explore. So we're really proud to share her story through this historic coin series, and we're really, really grateful to the Rubin family for allowing us to help carry her legacy forward. Thank you to all of the partners that have helped as well to bring this celebration to light. And I'm really excited to share with you that each of you gets a little something as you leave. The United States Mint is making sure that as you leave, you get one of the commemorative coin boards that helps collect all of the American Women Quarters. They've got you started already on your coin board with a Dr. Vera Rubin quarter. So make sure as you leave that you get one of those. All right, so with this program, we're now coming to a very exciting part. We call it the traditional coin pour. We have brought with us, we have 2,000 quarters, and we're going to be pouring those into this amazing display, which you'll hear about in just a second. And so I have Dr. Cooley and Ramona Rubin is going to help me with that, so hang on one second. That's the sound of the quarters almost hitting inside the spectrograph. So the telescope would be up here, the light goes down the tube, and inside this box will be the spectrograph. And in fact, we have, you might be able to see it, you might not, but the spectrograph itself splits the light up into its colors. We've got a little mini one over here that's shining a rainbow over here. And it splits the light up into its colors. We call that wavelengths, and in those colors, or the wavelengths, you can use that to look at galaxies, and in particular the hot gas and the stars in galaxies, and you can figure out where the parts of the galaxy are moving away from you or towards you based on whether they're shifted to the red, away from you, or towards you, shifted to the blue. And so that enables you to measure a rotation curve of a galaxy, so you can figure out which parts of the galaxies are moving away, which parts of the galaxies are moving towards you, and all done in a tiny little box like this. So we're now going to put the quarters into the spectrograph. You wouldn't normally do this with a telescope. Don't do this at home with your telescopes.
All right. Good afternoon, everyone. My name is Ashley Yeager. I am an editor at Science News Magazine, and I wrote a biography of Vera Rubin and had the pleasure of meeting her and spending time with her. And I'm honored to be here to celebrate her life and legacy, especially this week when we saw the first images from the observatory that bears her name, and also with the launch of this quarter. I'm going to introduce our fantastic panel and then say a few words about Vera's life. So immediately to my left is Deidre Hunter. She's an astronomer at Lowell Observatory and was able to work with Vera Rubin at the telescope and make some of the amazing observations that fueled her work. And next to her is Priya Natarajan. She's the Joseph S. and Sophia S. Fruton Professor of Astronomy and Professor of Physics and the Chair of Astronomy at Yale University, and the former chair of the Women Faculty Forum. Next to her is Katie Coleman, an astronaut. She was the mission specialist for the Chandra launch. And at the very end, but not the very least, is Dominique Kroll. She's an astrophysicist at the Center for Astrophysics here in Cambridge. So when I was thinking about what to talk about to introduce our panel today, I was looking at the new images that came out and looking at Vera's quarter, and just thinking about how these images really reflect the values that Vera lived in her entire life. She was always curious. She never wanted to make assumptions. She always wanted more data on everything. And so I think it's those values that led her to become a groundbreaking astronomer, a person who helped usher in what I call a Copernican-like revolution in how we think about the universe, that the matter we know is not the full matter of the universe. There's so much more. And so I think the other thing I'd like to discuss today with the panelists is about how not only those values, how Vera used those values to explore science, but she also used them to interact with people and to become the mentor that she was. And I say that because I would like to say a direct result of that mentorship. I met Vera when I was 22, after I had finished my undergraduate degree. I was not an astronomer to be, but had the privilege of interviewing her for an oral history project, working at the Air and Space Museum. And the thing that caught my attention, and still catches my attention, is that when we sat down, she spent hours answering our questions, and then spent the time asking me questions and being curious about who I was and what career I wanted and where I was going in the future. And that doesn't often happen as a journalist. Usually you ask a person questions and you move on. So I thought that was something that really stuck with me, not only shaping my career, but also how I interact with people that I come across, trying to be very curious about who they are. So I think, again, it's those values that made her not only a groundbreaking scientist, but also an exceptional human being and a role model for so many. So I'm excited to dive into Vera's legacy a little bit more. And so I think, Dr. Hunter, Deidre, I'll start with you. You worked with Vera. Can you share a memory that captures who she was as a scientist and a person?
Sure. I want to share a story that sort of demonstrates her curiosity and perseverance. We were at Kitt Peak National Observatory, southwest of Tucson, and we were there to observe on the 2.1 meter, and we were doing spectroscopy. And the first night of the observing run, the dome was broken. It wouldn't rotate. You could open the slit, and you could move the telescope, so you could point the telescope out the slit, but you couldn't point it to the objects that you wanted to observe. So most astronomers, including myself, would have just, okay, I'll come back tomorrow night. But she didn't do that. Well, anybody who observes at the national observatories understands how precious telescope time is. Every minute counts. And Vera, because of her history of being denied even the opportunity to apply for telescope time, certainly appreciated it even more. And so she said, well, we'll just look where we can. The sky's going by. We'll just take spectroscopy of the sky as it goes by. Mm-hmm. And we did. And she took the data and she identified so there are absorption lines, there are some emission lines, and there are tables of transitions that you can look up their wavelength. And she identified every single line in the feature in the spectrum except one. There was one that she could not identify. It wasn't in the tables. And so when we got back to DTM, she called up a colleague who she thought might know this. And eventually, after digging and digging, she identified that line. And then I remember some discussions that followed about why that line had the intensity that it had. And that was Vera. She wanted to understand things, and she was open to new ideas, and she was very, very persistent.
Excellent, excellent. Priya, I'll ask you a question next. Your work builds on Vera Rubin's legacy, helping us understand the distribution of matter and dark matter in the universe. What's the next frontier in mapping the invisible?
So as you probably all have seen, the remarkable images, of the night sky, impeccably high resolution from the Vera Rubin Observatory that have just been released, are extremely promising in terms of the various scales on which we can see the distribution of dark matter. So Vera's work showed that in galaxies, only about 10% of the matter is in visible stars and gas, and the rest is in dark matter. And in larger scale structures in the universe, like clusters of galaxies, gravitational lensing, the bending of light, has shown that there are vast repositories of dark matter. So dark matter seems to be distributed on very, very small scales, as well as mountains, mounds, valleys, hills. And so the frontier now is to try and understand, after we have mapped out spatially this distribution, the detailed distribution, whether there's any clue there to the nature of dark matter, because that is still an open question. Although we have mapped it, we don't yet know it. And I think particle physicists have been looking for it, and we've come up empty so far. So it's a big open question what the actual particle is that constitutes dark matter. We believe it's a particle that was created in the very early universe, but we don't know which one. And so I think the quest is on, and for the detailed properties of that particle. So far, the standard paradigm, which she absolutely helped establish, which is that our entire universe is structured by dark matter. All the visible light that we see is actually structured by dark matter. It plays it's in the driving seat for the universe, right? And that's why her work was so transformational. That was a complete shift, because there's been a legacy of looking at the night sky, looking at stars, and I don't have to say it here, Harvard College Observatory, the plates, and a strong tradition of women having looked at the night sky, but that was not all. They were hiding. So I think now we are hoping that dark matter, and there's this other mysterious entity in the universe called dark energy, which we believe powers the accelerating expansion of our universe, and it countervails this dark matter, which is gravitational pull. So I think it's going to be very exciting. That's another unknown. So I think what dark matter is remains to be discovered, given the exquisite data that we now have. So I think it's a very exciting time.
And sticking with that, I'm going to jump down to you, Dhammika, because you're kind of the next generation. How has Vera Rubin's work on dark matter influenced the way you think about the cosmos and inspire your own work?
Vera Rubin's work on dark matter for sure changed fundamentally how, I dare to say, all of us, as you mentioned, think about the cosmos. She showed that we just were observing before just this very small fraction of the universe. And for me personally, I think generally astrophysics is a very humbling science, because even not thinking about the dark matter, we are trying to study the universe. And that makes you think very hard about the fact that we are just living in one planet, which is one of the 8 planets which are rotating around the sun. And sun is just one of the hundreds of billions of stars in the Milky Way. And Milky Way is just one galaxy in almost countless galaxies in the universe. So learning that all of this is still just the tip of an iceberg. And beyond that, there's this whole world of dark matter which dominates so vastly observable matter when it comes to actually ratios, and also not even bringing into the conversation dark energy, which when it comes to energy balances is also very dominative. So for me, it's very humbling.
And Katie, I'll ask you, so you actually literally put Chandra Observatory into space. How does it feel to know that observatory, there's a lovely picture up here, that observatory really kind of gave us that first direct evidence that dark matter exists with the image of the bullet cluster?
So And I love this picture of all of us, partly because it shows some of the people. I mean, we've implied the people and we've seen pictures of Vera, but for every discovery, I think it's something that's not always so well known in the general public, is that science is a team sport, and there are many different kinds of people associated with that, and it seems that like Vera really understood that you needed different kinds of people with different perspectives. And so at the time, I will say I didn't understand. I knew that this was the telescope that might show us what dark matter was, or that we would learn more about it. But what really stuck out to me, because I think I was at a less advanced state, right, of knowing what needed to be known, was in being assigned to this mission, I of course started to learn about X-ray astronomy. And there's a book by, I think, Seward. This sort of was the basic, what we knew, not much back then. Still, it was a lot for me to get through. And I asked the guy on the very top in the silver hair on the left, Steve Hawley, Dr. Steve Hawley, an astronomer. I said, Dr. Steve, or we call him Dr. Stevie. Dr. Stevie, so you described like white dwarfs like this, but then I was reading this other book and they really said they were like that. And he said, well, Katie, when was that book written? And I said, 1986. And we're deploying Chandra in 1999. And I know it's not rocket science, but it was a revelation to me that the textbooks could be old so quickly. Like, I had to finish Seward's book before we got done with the mission, because clearly, I mean, X-ray astronomy was going to be taking off and the whole world would be changing. And so I've really liked being part of that journey. We were a 5-person crew. Every one of us contributed. The woman on the left, on the bottom there, is Eileen Collins. She's the first woman to command the space shuttle. Our shuttle, actually, with our very, very precious $1.8 billion cargo, the heaviest and the largest thing that the space shuttle, had ever taken to space. So it had significant technical challenges, heavy and all those kinds of things. And we actually had a very exciting, not in a good way, ascent up to space. We had an electrical short just seconds after liftoff and a leak in one of our main engines. It's known as one of the most dangerous ascents in the history of the shuttle program. But I don't think you hear that much about it, because I know that out of our crew, probably Eileen and I are a little bit more out and sharing than the others. And neither one of us are, like, I don't often say those words. I'm learning to say those words because I realize people don't know unless you share your stories, right? And people might have wondered whether the first woman commander would do okay in that situation. She did marvelously, as did Mission Control. But, I mean, not all 8.5 minutes later, we're in orbit, we are safe, all 5 of us. And I said, Eileen, are we deploying the telescope today or not? Because you have to go from one thing to another. And so I really was always so honored, and I think the 5 of us being up there, it was very emotional to be just 5 people that got to see this telescope where it was designed 25 years earlier. And so science is this, I mean, it's this long journey in every telescope, and I'm understanding that the Vera Rubin was designed, or the design was conceived back in the early 70s. And this is a normal timeline for I say this as an outsider, and y'all can jump in and say different things, but it's a long process, and there's lots of different people associated. And what I think is really important is that along that timeline, each of the people that are there have the possibility of creating ripples as they go along. And certainly the Chandra X-ray Observatory, the way I describe it, there's better ways, she's a Chandra scientist, but is that literally everything that we know about black holes comes from either Chandra directly or the cooperation between these telescopes together.
I think you would see that in Vera's work too. She collaborated with radio astronomers. There's theoretical work happening around the same time that she was making her discoveries. But I wanted to ask you, Deidre, what do you think was unique about Vera's approach to observational astronomy that set her a little bit apart?
Yes, the first thing is that she wanted her data to stand on its own little feet forever. And so she was very careful in her observations and in her measurements to make sure that they would stand. Interpretations could come and go, but her data would always be there to show this is the way things are. You know. The other thing that I've asked myself, and your book about Vera contributed to my thinking about that, was what made Vera's contribution transformative. Zwicky, many decades before, had observed that there was a problem with clusters of galaxies, that they should be not held together, they should be flying apart, and that there was missing mass. I don't know if he used those words, but so he was the first person to really see that, but people ignored his observation. I think what Vera did that was different was she didn't just observe one spiral galaxy, she observed a large sample of galaxies at different morphological types, different masses, and so there were all these galaxies that she observed, and dark matter was a part of every single one of them. This was overwhelming evidence that astronomers couldn't ignore anymore. And so I think that's why her work was able to transform our view of the universe.
Okay, I think, excellent. Priya, in what ways does Vera's empirical foundation for dark matter challenge or inspire your theoretical modeling?
So I think it was Vera very clearly understood. First of all, I had the real privilege of getting to know her when I was a young graduate student and I was giving my first talk on a new finding in how dark matter is distributed on small scales. It was an October conference in Maryland. And I was quite nervous giving that talk, and there was a lot of pushback and aggressive questioning. So she came up to me afterwards, introduced herself. I, of course, knew who she was. And told me, well, don't worry, the pushback is really good. It helps you refine things better. And so I stayed in touch with her, so I'm really deeply grateful. And I think your grandmother was amazing as a human being as well as a wonderful scientist. I think what she understood really well is that progress comes from the interplay of ideas and instruments. So you absolutely have to have data. And the ideas, the theoretical idea, the foundation, has the data rules. Basically, it's the data that tells you and confirms and validates an idea or a theory. And absent that, no matter how beautiful the elegant mathematics is, or the symmetries, or whatever else, about the theoretical idea itself sounds very plausible, that's not enough. And the fact that, empirical data really rules, and that you need a lot of good data, and I think as Deidre pointed out, she was very meticulous in showing that, before you make a claim that dark matter, there's evidence for dark matter, I know, reading about her and her work with Kent Ford, that they actually had the data for several years and they sat on it, they were thinking about it. They knew that this was such a momentous claim of something else that was invisible in the universe, right? And they took 3 years to quietly sit and then publish when they had a full sample, as Deidre outlined, full morphological span, various masses, various kinds of galaxies, and it came out to be the same ratio. So I think it's a certain kind of empirical rigor and driving that informs the field now. Mm-hmm. And the quest has been to simultaneously push for really high precision data, better and better data, and more data. Higher volumes of data, a lot more data, spanning the entire night sky if possible, and then working with very sophisticated ideas. So cosmology is a particularly weird field in the sense that, as Dominica pointed out, we live in the universe that we are trying to study. It's not an object that we are outside. We cannot replicate any observations. You can't, unlike chemistry, you can't keep redoing the chemical reaction. So what you have is what you get, right? And therefore, simulations, computer simulations have started to play a very important role in validating what is seen in the universe. And I think that Vera's ideas of the potential existence of this missing matter as dark matter really has run this revolution of cosmological simulations, because it gave us a starting point. Like, you have 90% of the matter is dark. Now let's place 10% as ordinary matter that we are made of, and let's see how the simulation runs forward, and do you make galaxies like the ones that we actually discover. So there's a kind of empirical rigor that, that she exemplified that actually characterizes a lot of the work in dark matter research, for sure, and all of astronomy. But in particular, dark matter research, only because it remains elusive. So we are still really trying to push the boundaries and to find multiple independent ways to characterize dark matter. So along with the rotation curves, as I mentioned, gravitational lensing, as well as the clustering of galaxies, lots of independent probes to see if we can get any hint on the true nature of dark matter. So I think it's a legacy of a particular kind of meticulousness and rigor, and also a desire to always have the data speak. I mean, she was very fond of the theorists and theories and ideas, obviously, but I think she realized that the ultimate test in the universe is whether something can really exist, not that you would like it to exist.
Right. Well, we talked about her spectrograph a little bit. Dominica, I was going to ask you, what are some of the tools or methods that you're using that Vera Rubin couldn't have even dreamed of? Something that's helping us answer questions she raised.
I mean, 50 years ago, when she was gathering data for her discovery, it was completely different stage of technology. The observatories, which we have right now, have much better resolution, so what basically can see much more details of the universe. We also have detectors which are able to detect much fainter sources. So in a lot of cases, it means that we can basically observe sources which are much more further away. And as it has been mentioned before, there are all of the computational resources which we are using. But I think what I would like to focus on is actually the multi-wavelength approach towards astrophysics and astronomy in general. Because the optical light, as we call it, is just a very small part of the whole electromagnetic wavelength spectrum. And that's the part which our eyes can see. So that's why historically astronomy was the science which was focusing on the optical observations. However, only combining different wavelengths can give us a whole picture of the universe. So except of the optical data, now science is also focusing on radio data, infrared data, UV data, so ultraviolet light, infrared light, X-rays, and gamma rays. And I am studying mostly universe through X-rays. So the Chandra is a very good example of the observatory which changed the way we see the universe and also helped to probe the dark matter. And one of the pictures which is circulating here is the picture of the bullet cluster. So bullet cluster, oh, that's exactly. Here is a perfect example of how combining different information from different wavelengths can give us information which would be inaccessible with just one. So clusters, this collection of galaxies, are filled with a hot gas. Gas is so hot that we can observe it only in X-rays. And what you can see here is in pink, X-rays observations from Chandra, which are showing where is the gas. And then you can see the galaxies, which are visible in optical light. And in the purple, you can see, I believe, if this is a color coding, which usually happens with this picture, in purple you can see the distribution of the dark matter. And what we see here actually is the collision between two galaxy clusters. So this was, first of all, a very convenient evidence for the existence of the dark matter, that thanks to the optical lensing, gravitational lensing, it was possible to see that the center of the dark matter is there and that a lot of the mass is in the dark matter. But second of all, it allowed to put limits on the interactions of the dark matter, showing that the dark matter is moving forward more than the gas, which is lagging behind, interacting with each other. So it helped us learn about the dark matter, that it doesn't interact with itself or the visible, baryonic usual matter. So right now we are not only using multi-wavelengths in order to observe the universe, but also even gravitational waves, right? So what I would say multi-messenger even approach is common right now. So all of those tools are allowing us to explore the questions which Vera Rubin were asking in much greater detail.
There's a much broader set of data beyond observational
Yes.
astronomy to still be tapped. Okay, excellent. I think maybe we'll talk a little bit about Vera as a human being. And Katie, I'll ask you this question. Vera very much thought that humility was important in science. And so I was just going to ask you, as a scientist, as an astronaut, how does that factor into to your thoughts about Vera's legacy and also the field of science?
Well, I think humility is important, and also, well, one of the things that I try to remember is to always assume good intent of people, right? But I found myself, since I'm not quite from your community, right, in talking about Vera's always making sure that she's really thoroughly just answering every single question that actually anyone who really wants to know what's going on would want to know. But is there ever a part of that is that she had to have things pretty perfect in order to be believed? Because it was a time when there weren't many women's voices?
Absolutely. And I think not just as a woman, but anytime you present a radical idea, no matter who you are, because the way science works is that we all interrogate ideas collectively, we question, and then through a real process of contestation, amicable mostly, you reach consensus. Mm-hmm. So anyone who comes up with a radical new idea actually faces a lot of pushback. And I think, definitely in her time, it's not surprising that, as such a, the sort of first woman to be breaking all those barriers there, she probably had to be even more thorough in order to be persuasive. Even though the data spoke, she really had to. And also, I think that discovery of dark matter as such was so momentous, it was so transformative, it completely reshaped our understanding of the cosmos. So the implications were just profound. So I think she kind of knew, although she couldn't probably foresee everything that happened after, but she had very good instincts. So she could see that if this was right, it was very, very important. And so she had to get it right. She had to get the interpretation of the data right.
I hear what you're saying. And I think that humility actually invites other people into the field. I know for me today, just to learn more about Vera and, from her granddaughters, and I like to understand that these people that you've heard so much about are actually human, that this is a dress that your grandmother actually loved, right? Excuse me, and that they're real people. I wondered, so this is in terms of what you talked about, what it means to learn so much about, to use X-rays to learn about dark matter. What happens when, like, for example, Chandra, in the proposed budget, which we don't know if that'll be final, but there's certainly threats to Chandra, right? What happens to learning about dark matter?
And black holes. We hope that it's a temporary pause and other instruments, new observatories, new initiatives will take their place. I think we hope science marches on.
Are we in year one of the 25 years of the new instruments? Or do we have something that's
there are proposals that have been funded for further study, both in the infrared and X-ray probes, which are not these sort of flagship missions in the United States by NASA. We don't know how that's going to unfold, but the Europeans have a strong, thriving space program, and they have a telescope. They have an X-ray telescope called Athena, which is in the works to fly in the 2030s. And they also have LISA, this speaking of multivalence that Domenica talked about, a telescope, a sort of a 3-satellite sort of formation in space that can detect gravitational waves from merging black holes. And that's on course for 2030s. Again, that's a European-led mission. So I think that we're at a very interesting point in sort of Americans, sort of our leadership, intellectual leadership in astronomy and astrophysics. And I hope we actually seize the moment. And the current, what's going on right now is just a little bit of turmoil, and that we get back to where we are. Because I think there's a lot of us, I came to this country as a young person, grew up in India, and I think there are a lot of young people around the world that have looked to the United States and looked to these incredible missions, Hubble, Chandra, now James Webb, and are super inspired to do science. And they may not end up as astronomers, but they end up doing science and technology. And I think we live in a world that is completely permeated by science and technology. And so I really hope that this is temporary and that we are back in gear very soon.
No, I like that quote that Vera had. I won't say it exactly, but it's that we've learned so much, but there's still so much more to learn, and that's for the generation of curious explorers that are coming next.
Yeah. I think Vera's work definitely inspires, and it did inspire and will continue to inspire future generations. So I was going to ask you how Vera's life and work shaped your own path in astronomy.
I was a postdoc, and I had applied for a second postdoc position at various places, and DTM offered me a job, and I accepted. That was sort of February of whatever year, and but I didn't go until August. This is the standard academic calendar. In between February and August, I decided to leave astronomy because I didn't like astronomers and I didn't want to be like them. Now, looking back at it 40 years later, I really don't know what I was thinking. But I had accepted the job, which is a commitment, and I was going to do it. So I went, and I thought, okay, 2 years from now, I'll decide what to do with my life. Well, I got to DTM, and I met Vera. And Vera, as we've been talking about, she was this person who changed our view of the universe. And yet, she was kind and supportive and unassuming and helpful and all those good things. And she was relatable. She was a down-to-earth person that you could relate to. And all that negativity I had come with just melted away, and I never thought about it again. And so, here I am, 40 years later, still doing astronomy, thanks to Vera.
I'll follow up on that question for you, Priya. Vera often spoke about how we needed change in science and to be more inclusive. And I wondered, and Dominica, you can also weigh in on this, have you seen that change in the field? Has it gotten better? And if not, or if it has, or if it's not, what's still missing?
So, I think things have gotten much, much better. I think that a lot of the obstacles and struggles that her generation had to deal with, even by the time my generation came along, she opened the doors. That generation opened the doors for us. And I think my generation has tried also to make it more inviting to younger people. So one of the things that so I personally was involved with was anonymizing, dual anonymizing proposals for telescope time on the Hubble. So we did this experiment with just allocation. So, scientists who want the Hubble Space Telescope or the Chandra to look at any particular part of the sky have to apply for time. So it's a very competitive process. You put in your request, and it's judged by peers, experts, reviewers, scientists, and then they sort of rank the priority, how important this science question is, whether this is the appropriate observation, and so on. So it turned out in the Hubble Space Telescope, they had done a study of who gets time. And it was very skewed in terms of, I don't have to specify, I think everybody knows. It was very skewed. It was also skewed not just by gender, but also by the institution, the kind of place that you came from. So if you came from a smaller college, for example, it appeared that there were other, and age. If you were younger, not as established, you were less likely to get time. So they noticed that there were a lot of these issues that pointed out that it was not equitable. So they said, okay, let's do this experiment. And so I was involved in the rollout of the first time, and they said, okay, we have a dual anonymous. So you don't know who is applying, you don't know their institution, you only know the idea. And so proposal doesn't have the name of the institution, the person, but you have to make the scientific case. And I remember the pushback was, at the time, someone said, well, what if an 11th grader from high school just, puts in a proposal? And I thought, that's fantastic. We should give them the time. If an 11th grader can come up with something that persuasive, right? So I think dual anonymous reviewing of proposals. And it was incredibly successful. Even within the first round, you could see that it had sort of leveled the playing field. And I'm really thrilled to say that, and this is something that I know that she would have been very, very proud of, that my generation pulled off. It doesn't solve every problem, but it's low-hanging fruit. And this is now the procedure that's been adopted for all proposals, for allocation of all resources, pretty much, in astronomy and astrophysics and beyond. And even in Europe and everywhere else there, this has been brought in as, so one gesture to one kind of intervention to level the playing field. I mean, there's of course much that needs to be done. Part of the problem, I think, and I think what Deidre alluded to was like the culture of the field and everything, is the scarcity of resources. I mean, the scarcity of resources, impacts the mindset. Aside from the fact that, science, by very nature of the kinds of questions we ask, and curiosity and independence that it takes to be a scientist, attracts a very particular kind of personality. So I think what has been really nice is the move to collaborations that's happening recently. And I think there, I'm reminded of this wonderful interview that Vera gave to the American Institute of Physics. They do these archival interviews. I recommend everyone to go listen to them. They're absolutely fantastic. There she talks about how, without Kent Ford, her collaborator, building that instrument, and these observatories agreeing to put that instrument on these big telescopes, and all that infrastructure that was needed, and the many, many people who had contributed to every step of that, she could not have made the discoveries. And I think that is playing out now like big time, right? The Vera Rubin Observatory, thousands of scientists, engineers have participated in making that happen. So I think the collaborativeness of science, of course, that brings a different set of problems when you have to collaborate with large groups with different talent sets. But the questions have become more complex. We know a lot more, although we don't know what dark matter is quite yet. We know a lot more about the cosmos. And so I think that she would have been really thrilled to see that collaborations are now acknowledging the contributions of a lot of the unseen people. People, especially people who build instruments, don't often get credit for the scientific discoveries that are made with those instruments. Because it's not instant, it takes time, and it takes teams to exploit every feature of these very sophisticated instruments. So I think the changes are very positive, and I'm an optimist, so as you can all probably tell from my previous comments, right? So I think things are moving in a really positive direction in terms of collegiality and the sort of shared credit for discoveries. But there is more room for things to be done. I think what would be great if every kid growing up anywhere in the world who is enthralled by the night sky and feels that they would like to explore being an astronomer, I would just love for them to have a chance. They may choose it, they may not, but I think they should feel that if they have that dream, that they can, pursue it.
Dominica, do you want to follow up on that question too?
I would like to actually connect to the last part which you mentioned about the collaboration. What I think is also very important and really helps is the huge shift towards open access and archivization of data. So for instance, in the biography which you wrote, Ashley, there are recollections of the fact that Vera Rubin had issues. I mean, first of all, as we heard already multiple times, she was not allowed to access observatories and observe by herself because she was a woman. But also, when she was preparing her master thesis dissertation, she had issues with accessing the data. She wanted to have more data. And right now, all of those amazing experiments, all of those observatories, or at least vast majority of them, have archives which are public. So there is, of course, the system of the observer's times in which somebody can apply for the observations, and then they have this data for some short period of time for themselves. But later, after half a year or a year, all of the scientists around the world can download the data and they can try to make their own science. And I think it really helps because everybody in the scientific community have at least access to the data which are coming from these very cutting-edge instruments.
Excellent, excellent. Katie, as someone who's flown in space and worked in chemistry and robotics, what advice would you give?
What a fan of astronauts. All right.
What advice would you give to a young person hearing Vera Rubin's name today?
Most important is that if you want to be an astronaut, everyone has to be something else first. And it should be something that you feel passionate about, that you just want to know things, which I think you sense in all of these people, including yourself, you know, very curious and also really wanting to communicate. I wrote a book about my NASA experiences, partly because I feel like as an astronaut, they don't belong just to me. It's really clear once you get pretty high up in the selection process that there are really a lot of people that are qualified, and there's a sort of time and space, and I felt qualified, and I felt very, very lucky to be there and to be able to do those things. And at the same time, some of the things that you talk about are familiar to me in terms of having to be sure that you present things in a way that someone else can hear them, and that you have to be better still. And you know, as much as I really loved being there, and I flew twice on the space shuttle. I spent almost 6 months up on the space station, and my husband's here in the audience. He knows that I would have spent another 6 months in a minute. And I really, you know, in different ways, you know, loved the people that I worked with, both men and women. But you know, I started off in science where, as you were talking, I thought, I still remember. I had got a PhD in polymer science and engineering. And I still remember we had seminars that would happen, sometimes twice a week, at least once a week. And I still remember when a woman professor came during my 5 years there, the only woman professor. And I said, you know, I'd really like to meet her. And my professors who were younger, we had these kinds of discussions, which I found very positive, that we could talk about these things. I said, Katie, why does it matter to you? I mean, is it because her research is exactly what you want to do? Why does it matter that she's a woman? I said, well, I just think it'd be nice to understand who she is and what, you know, I could feel like I could relate to her. So I think that in your future, it makes me feel better when I hear people's stories and I realize that I'm part of a larger effort to make all of our voices heard, and that something that's hard for me might not be hard for someone else, and I can learn from that, and they can help me. And so I think realize even if you kind of like working alone, the field and the research that you're doing, or the purpose that you've decided you have, is more important than you doing it alone. You're going to need collaboration and people that you work with, some of whom you will love and some of whom you will prefer. We're different, but you're still about the same mission.
Mm-hmm. I'll ask you this question. Were there very few women when you started in your career? Was Vera the first that you encountered? You talked about your experience being very frustrated with the culture.
Yeah, well, about when I was in graduate school, people We're talking about role models. They began, that was when they first started talking about role models. And I thought, I don't need a role model. I have a great thesis advisor, and what does it matter? What does it matter that he's not a woman? Then I met Vera, and I said, wow, this is what a role model is. And this was exactly what I needed.
Yeah. That's excellent. That's excellent. In terms of your work now, can you talk a little bit about how that's grown out of your work with Vera?
Well, I think not just me, but the field as a whole, no matter what you're studying, maybe not no matter what you're studying, but a lot of what people are working on. I'm interested in how little dwarf galaxies form clouds that form stars. And if you want to understand that, you have to look at the environment in which the cloud formed. Well, now there are these components of galaxies. There are stars, there's gas, and there's dark matter. And you can't always ignore the dark matter. And so that's just standard. People take that as a component of galaxies that you have to think about.
Okay. Priya, I'll ask you this question because we talked a lot about Vera's story and storytelling and how important that is. How do you think we can continue to use storytelling to push Vera Rubin's legacy forward and also other women scientists for future generations?
I think, obviously these kind of commemorations are really important, keeping their memories alive, their work alive. And also, I think, really writing and reading about them. So telling these stories of these women who shattered many glass ceilings, I think just keeping their stories alive because they are relevant and pertinent. Even if the science has moved on and has become much more sophisticated, the ideas have been supplanted, like in science, any idea runs the risk of, everything we know is provisional. I think just keeping their memories, their stories alive, keeping track of not just their intellectual contributions, but the kind of thing that we're doing today, where we're trying to understand the person, the human being, and the impact that they've had on others. And I think the younger generation today really does understand what role models do for them. And I find that the younger generation is very sophisticated. They understand the difference between mentors and sponsors, people you can talk to and people who will speak for you. And so I think role models remain inspiring even as we live in a social media driven age and where the means of communication have moved beyond just a book or a movie. So I think that, telling stories about their science, which is also very important now. At this moment, there's so much denialism of science that, highlighting the science that they did, the work that they did, as well as who they are, I think makes a big difference, especially for these women who really were sort of who broke a lot of kind of norms that constrained them. And I think that, it does make a big difference, having these narratives and having multiple narratives, having a lot of different kinds of people talk about these people and how their lives and their work have been impacted by these sort of pioneers.
And this is probably for anyone who wants to pick this question up, but you mentioned not only talking about her science, but also talking about her life. Why is that valuable to see the whole person versus just the scientific achievement?
I think that it's because at least speaking for myself, when I'm thinking about what to do next or how to have to regroup after maybe something wasn't successful or making choices, I'm a person and I have to, inside my head, I have to make those choices and have to figure those things out. And I'm made up of a person that has a family that likes I like music, I like people, I like the laboratory, I like all of these things. And the fact that you can mix them up and that they can work together. I make a point of showing my poor family, I show them in my presentations all the time, partly to make a point that I have one, and that means that maybe you could have one. And when I interviewed to be an astronaut, one of the senior women, one of the first 6 women to be selected as astronauts, Ray Seddon, came over to me during the sort of time we're supposed to relax and just be at happy hour, which you really know you're still being very judged, right? And she said, Katie, I just want you to know, you may not even be thinking of this, but if you want to have a family, you can do that here. And we are a family and we will help. Each other. And that meant the world to me. First of all, that she spoke to me and seemed to actually, think, and I really hadn't thought about it. Sorry, sweetie. So I just think it's really, we're whole people, and it's easier to understand how we could fit in that world if we can see a whole person.
Yeah, it's an interesting perspective because it's not something that's often told when we talk about male scientists.
I mean, I will say that there's times at work that I just felt like, I'm just going to go into work. I'm not going to have washed my hair. I'm going to wear glasses that I don't need. And have my hair sort of stringy in a ponytail. I'm not going to ask anybody about their day standing at the elevator. I am just going to do my work. It usually lasts about most of a day, and then I forget, and you become yourself. But I found that it was hard for people often to sort out that the person who was good at explaining things maybe to the media or whatever was also very good at their job. The same as the people who didn't say much but did their job.
I think it's also about possibilities. I think you're able to dream, right? I mean, I think a lot of, it's almost like giving young people the permission to dream. So the more you know about the different kinds of people, what they do, what they've done, what you can do yourself. It's about the possibilities, I feel, that role models really make a big difference.
Yeah. And I think in general it's very inspirational, especially in the fields which were historically dominated by men. For instance, learning physics in university, I remember first time reading about Vera Rubin exactly in the context of the discoveries she made. And thanks to this, it was much easier to dream about being a scientist because it was showing that part of the science right now is shaped by a woman. And especially later on, reading more about her life and making this picture a whole and learning about how difficult it was for her, how many struggles she had, how she could not access observatories, I remember this story of her being asked to enter her own lecture through the side door because the club in which she was giving a lecture was not allowing women to enter through the front door. And all of this really makes you realize how big of a struggle it was. And you can, first of all, you see how far we went, how many role models are now around us. And second of all, it really helps to try to, as you mentioned, Priya, dream about becoming a scientist.
Yeah. One thought that comes to mind in researching the book was the idea of Margaret Burbage being Vera's role model. And it wasn't something that I had thought about until I started reading. And so then that wanted me to go read more about Margaret Burbage.